All right, everyone, I guess we'll get started. Seems like it's about time. Welcome to the first recitation for 10703. I'm Brian. This is Raj. We are two of your TAs this semester. For this recitation, we're just going to be going over mostly stuff that hopefully you've seen before, but if not, it's okay. This is just a quick refresher. We're going to spend a lot of this recitation talking about neural networks and deep learning, just so you get familiar with that, because that will be probably most of the class in terms of homeworks and implementation. Talk briefly about TensorFlow and PyTorch, talk about Gym, and then also Bandits, which will be the first homework. First, before we get started, I guess just for people in person, can you raise your hand if you've used PyTorch or TensorFlow before? So you get a general. Okay, cool. How many of you have used PyTorch or TensorFlow to do like a deep RL thing, like something related to something in this class? Okay, cool. All right, sounds good. Yeah, we'll hopefully not spend too long on the basics, but we'll just kind of breeze through them, just make sure that you're kind of familiar with these things. All right, cool. So we're going to start off with some just sort of high-level motivation-y type stuff. So this class is about deep reinforcement learning. And so I guess to motivate sort of why deep learning is useful for this sort of field of research, there's this quote from a bunch of Turing Award winners that basically talks about how deep learning is basically fundamentally about representation learning and using multiple levels of representation that are sort of automatically learned from like really large data sets. And principally, these methods are composed of a lot of these sort of simple but nonlinear modules that you stack on top of each other and sort of gradually transform a representation from your raw sensory input to some higher level, more abstract representation. In the context of decision making, what this looks like a lot of the time is for policy, for instance, where you might go from an image of a car or like a driving scene, pass it through a neural network that sort of gradually transforms this into some higher level, more abstract thing, like a driving command or like a motion command. And so the main benefits of this is basically that this scales really well with large amounts of data and that this is sort of less reliant on manually engineering features. And as we will see, these are two very big issues when it comes to applying classical RL techniques to real world problems. So now we'll talk about why this sort of motivates specifically deep RL and why RL kind of benefits from the use of these deep networks. So traditionally, and I think this will be a lot of the beginning of the class, classical RL techniques rely on really, really simple function approximators or ways of representing functions. A lot of the time, we're literally talking about lookup tables, like not actual, like, smooth functions that can approximate continuous things, but literally dictionaries, or in some cases with simple linear functions. And basically, all deep learning does is allow us to handle much more complex functions. In terms of the sort of underlying RL theory, the algorithms we're going to be talking about, most of what we're going to talk about in this class, you could hypothetically do without using any deep learning at all, but deep learning is just kind of a useful tool, and so we're going to talk about it a lot in this recitation. In terms of why function approximation is very useful for RL, it allows us to represent, I'm not sure if we've talked about these things, but like agents, reward functions, if you want to model the dynamics of the environment, you can do all these things pretty easily, in some cases using deep networks. And it also allows us to handle much more rich input modalities. So a lot of classical RL pretty much only works on very simple low-dimensional state representations that are like not very big vectors, but using deep learning, you can start learning agents that actually function over things like images or text. So yeah. Cool. Again, hopefully you've seen a lot of this. If not, then I don't know, maybe go over these slides in your own time or come to office hours, but hopefully you guys are all familiar with multi-layer perceptrons or MLPs. These are the basic building block that we will be using for pretty much all of the deep learning stuff you will do in this class. It'll just be some variation of training an MLP, nothing super fancy. On a high level, it's basically just a nice universal function approximator that we can use that will just map vectors to vectors. It's very general purpose, and it doesn't have any strong inductive biases. So everyone here know what an inductive bias is, or can somebody offer like a quick definition in case people have not heard this? Somebody have that? No? Okay. So an inductive bias is basically just any bias that it is basically something that helps your model that is not in the training data, essentially. So it's like a bias built into your model structurally. So if you're familiar with, like, for instance, a convolutional neural network, which I guess we don't have a slide for because it's kind of out of scope for a little bit. A convolutional neural network has an inductive bias, which is spatial locality. So like similar features near each other basically are basically the same. Basically, you apply the same filter across the entire image, and that sort of induces spatial invariance. The same feature that happens in the top left of your image might be the same at the bottom right. Basically, inductive bias is just like anything that helps your model that is not in your data. And as it turns out, MLPs have very few of these, and that is actually kind of a good thing because it means that they can approximate sort of arbitrarily complex functions without needing to do anything else. Fundamentally, MLPs are just a stack of feed-forward layers, which are composed of like a linear layer and then some nonlinear activation. And the representation for an MLP is hierarchical. So you can see that it sort of goes from an input layer, which is like your input vector, to some sequence of hidden layers and then an output layer. And each vector at these sort of intermediary stages is also sort of a representation of your data and something that could potentially be useful for basically like other things. And it sort of is a just different encoded representation of your input, just at a different level of hierarchy. Now, if this is all super obvious to you and this is all like, this makes sense, this is basically all you will need architecture-wise to do all the homeworks in this class. So if this makes sense, congrats. That's pretty much all you need. We're going to be going over some more complicated things that will show up in the papers that we're going to talk about in this class. But in terms of implementation, I'm pretty sure it's like 99% MLPs.
Just as a point of order, the slides are now on the website, so if you want to follow along, the slides are perfect.
All right, cool. Any questions about anything we have talked about up to this point? Okay, cool. All right, here's some math. I'm just going to skip this because it seems like you guys know these things. Okay, cool. RNNs, again, hopefully you've seen this, but this will be kind of useful for a lot of the papers we're going to be talking about. Basically, the only difference between RNN and MLP is that an RNN has a recursive operation where basically, instead of just having, for instance, on the left, this MLP that predicts an output from the input, you also predict basically a hidden state that you will pass into the next operation. And this is sort of useful for, as you might guess, sort of sequential tasks where you have, for instance, the need to maintain an internal memory. And so RNNs are often super useful for, in one case, representing an agent in partially observable environments in particular, because in those cases, you need your agent to sort of intuitively have the ability to keep track of what it's seen before. And so RNNs end up being sort of theoretically useful there. Beyond that, they're also sometimes useful for modeling dynamics, for instance, in environments where the dynamics are not just Markovian, but they are not just dependent on the previous state, but they're sort of sequential in nature, and you have like long horizon things you want to model, and so you might use an RNN. Okay, cool. So again, this is a very natural fit for decision-making problems, but sort of counterintuitively, in a lot of RL applications, using an RNN is actually a very bad idea. And I guess we'll kind of get into the reasons why that's true later. But basically, what it boils down to is that, I guess, for all intents and purposes, RNNs have like this kind of major problem, which is that they, even though their entire goal is to sort of keep track of historical information, they often have a very hard time of actually attending to information that you've seen many, many time steps ago. And this is partially alleviated by like more modern RNNs like LTMs and GRUs. But this is still sort of a long-standing problem, and a reason why RNNs, while like sometimes used in RL, are not actually super common, even though they seem like a very obvious fit for the problem we're talking about. RNNs are also kind of hard to parallelize because they sort of happen sequentially. So in order for you to compute like your hidden state in like 10 time steps, you need to like go through all the time steps and generate those hidden states. And so they're kind of slow. All right, any questions about RNNs? Okay, cool. All right, since this is going pretty quickly, we're going to talk about attention and transformers. To be clear, you will not be, I don't think, required to implement any of this, but this is mostly because I think for Katerina specifically, a lot of the papers that we're going to be talking about for the later half of the class will be about this. And I don't think we're planning on covering this in lectures, so we're going to go over this a little bit now. And if you haven't seen this before, that's fine. We're just going to do a complete intro. So can anybody here, I guess who here has like worked with transformers before, or like attention layers? Okay, cool. Okay, so basically, attention, you might have heard of before, is basically the basic building block used in transformer models. And transformer models are like, I want to say this new hot thing, but they've been around for like 5 years. So like this like thing that's been around that is fairly state of the art in a lot of tasks, specifically in like natural language processing. You can basically think of an attention operation as being a sort of differentiable dictionary lookup that takes in 3 vectors. And that's a query vector, a key vector, and a value vector. And so every single argument that you input to an attention operation is just a sequence of vectors where they're all the same sequence length. And the output is also a sequence of vectors with the same sequence length. And so there's only 2, I think, very important differences between this and sort of the standard MLP stuff that we talked about before. The first is that the sort of intuition for why attention is good is that it can selectively attend to and ignore specific sequence elements. So this is something that MLPs don't do. MLPs basically don't, in a traditional sense, like pay attention to specific parts of your input. Even though standard feed-forward layers can kind of like do a lot of the same operations that attention can do, I think the difference is basically sparsity. So in an attention operation, they can basically very easily pay attention to very specific elements, ignore everything else, whereas MLPs are very sensitive to every part of the input. And this becomes very important, especially in domains like natural language processing, where you kind of do not want to process the entire input equally, but there are very specific words, for instance, that you might care about. And in the context of RL, this is much more important when you move into, for instance, input spaces where you have a ton of information you need to process, but you only really care about a few specific parts of it that you sort of want to process for doing reinforcement learning. The other thing that's really nice about this, and I think probably more practically relevant, is that attention can handle arbitrary length sequences of vectors. So whereas MLPs, as you might know, sort of have a fixed input size that you kind of can't change because all of your like weights are like fixed size matrices. In attention, you don't have that problem. You'll see that when we kind of go over some of the math or talk about some of the math later. But basically, they can handle arbitrary length sequence inputs. And so that helps it sort of adapt to not only domains like, I guess, language, but also it's just kind of useful for handling lots of domains where you might have like an arbitrary number of entities or other things in the environment that you want to model. Okay, that was a lot. So is there any questions about anything attention related so far? Okay, cool. Okay. So this is sort of the basic kind of like specific kind of attention that we're going to be talking about. There's a lot of different kinds, but this is like the important one that most transformers use. So as we talked about, you basically have a query, and then you have key value pairs, and these are all a sequence of vectors. And the output is basically just the weighted sum of values, where the weights basically come from the queries and keys being multiplied by each other, taking the inner product. And it's the weighted sum over the values, which is again a sequence of vectors. So this is the exact equation if you want it. In practice, we actually use something called scaled dot product attention, which is basically the same thing, except you also divide the queries and keys by like their length. I'm not going to talk about why that's important, but it stabilizes things. And if you want, you can look at the paper. But yeah, this is basically just like the mathematical formulation of what we just talked about. Basically, this operation takes in your queries and keys, uses those to generate weights to sum over, to sum up your vector, which is not vector, your value, which is a sequence of vectors, and that gives you sort of an output to your attention operation. In practice, we haven't really talked about what Q, K, and V are, and it's sort of not clear because I feel like there's a big jump from that and sort of like natural language and not reinforcement learning. But basically, Q, K, and V are sort of computed from normally the same input vectors. This is called self-attention. Basically, if you start off with just a sequence of vectors, then you can compute Q, K, and V basically from them by like adding basically like a linear layer or doing sort of whatever you want. That can generate query, key, and value vectors, and then you can do the attention operation. Sometimes, and this is kind of important, you might not want to do self-attention, but the keys and values might come from another sequence of vectors. So for instance, in natural language processing, the clearest example of this is where you have like an embedding, but you want to attend to like another embedding. So like, for instance, if you're referencing like another document or if you're referencing like another pool of entities, then you might cross attend. In that case, you just change where Q, K, and V come from, and you basically just do the same thing. Okay, cool. And then in practice, attention sort of doesn't work very well if you just do it once. And so people will basically stack this a bunch of times. And so I think this diagram, at least in my opinion, is sort of the best illustration of this that I found, which is basically where, as we talked about, you basically generate your query keys and values by sort of projecting your sequence of vectors. And so you can just do that projection multiple times and then perform attention multiple times, and we call that like n-headed attention or whatever. And in practice, this is just sort of empirically useful. Anyways, there's a lot of tricks that go into making transformers work. We are not going to talk about most of them because they're sort of out of scope, but I think that understanding the sort of basics of attention, it will be helpful for some of the sort of papers we talk about later. Here's a diagram of what like the overarching transformer looks like, which again, I don't think you need to know, and we'll go into it later, but the sort of basic building block, which I think is important, is multi-headed attention. And so if you understand that, then sort of the rest of this can be easily put together. Okay, you can come back to this later if you want, but I think this is the most important part of this, which is like, okay, even if all that math was kind of confusing and not very helpful, I think that the important thing to think about is basically how transformers might relate to reinforcement learning and sort of why we're talking about them. The long and short of it is that even though that these models are sort of developed for natural language processing, they're very general. Sorry, question?
Can you give like a non-technical intuition of what Q, K, and V are?
Yeah, sure. Okay. Yeah, so I guess we can do, let's not do a natural language example. Let's do an RL example because this is an RL class. Let's say that you are, an environment where you have a bunch of objects. Okay, let's say that you have like a manipulation environment, like you're doing some grasping thing, and your environment is composed of like n cubes or something, right? Like just a bunch of objects, right? So basically the idea is that if you might have some way of embedding sort of each of these objects using, I don't know, some deep network or something and getting some representation of it, but you want to perform some operation that actually handles this arbitrary numbers of objects basically in the scene. Now you can't really use an MLP very easily because there are an arbitrary number of cubes. There might be 1,000, there might be like 100 or something, there might be one. And so you can't just like, flatten it and concatenate it and throw it into a vector. And so you might use an attention operation. So what we have here as our input basically is like a sequence of, if there are like n cubes, maybe you have n tokens in the sequence, and each token or vector has some number of features, right? And the idea is that basically query key and value, you can generate these vectors from this sequence of vectors. That sounds super confusing, but basically you can generate a query key and value all from this vector just by using different linear layers, basically. And intuitively, what each of them means is basically the value is like the contents of the dictionary that you're kind of looking up. But there's a lot of keys and queries or whatever in that dictionary, right? Or a lot of keys in the dictionary. And so basically you use the query vector and the key vector to determine what is the most important part of that value. So like intuitively, the value is basically like a sequence of vectors. And now you need to pick which vectors in that sequence are important or that you care about. And the way that you do that is by taking the dot product between a query vector and a key vector. And again, all of these vectors, because this is like deep learning land where things don't mean anything, all come from like the same sequence of vectors, basically, just using different linear projections. Does that kind of make sense?
So are these all assumed to be like from 0 to 1 continuous vectors? Or are they like on-off switches?
They're just like hidden features, so they can be anything. Sorry, not a very satisfactory answer, but yeah, I mean, they can literally, they're latent features from the network. So I think in practice, yeah, they do apply some normalization to them, though. So they're like, mean 0 or variance 1 or something. But but again, I think the best way to think of attention is like, it's like a dictionary lookup where you basically want to generate the things that you're looking for from the vector that you start with, the sequence of vectors, and the thing that you're indexing into is also your original sequence of vectors, if you're doing self-attention. Okay, I know that was probably confusing, but again, this will probably become more relevant later, hopefully. And if you have any questions, we can talk about this more. Okay, cool. All right. So I guess the main takeaway, if the math is not super clear, is basically just that transformers are like these like fancy models people have been using that use an attention operation, and they are very strong in like other domains. But the reason why they're useful is because they're very sort of general like models that you can use for a lot of tasks, not just natural language. As we talked about, being able to, for instance, process long sequences of states is not only useful for language, but also very useful for doing, for instance, reinforcement learning or imitation or modeling dynamics and a bunch of other things. The other thing that they're very good at, which we talked about before, is permutation invariance. Who here is like familiar with that term, actually? Like permutation invariance. Has anybody heard of that before? Okay, some hands. Basically, the idea behind permutation invariance is that if you have a sequence of vectors as your input to a transformer, no matter how you shuffle the ordering of those vectors around, you'll have the same output. So they're invariant to whatever permutation of the input. And the reason that is sort of very useful is because that is distinctly not a property that MLPs have. If you shuffle, obviously, like the features that you pass into an MLP, you'll probably not get the same output. But that actually is the case for transformers. And that is pretty useful, as we talked about, in a lot of real world settings where, for instance, there is no natural ordering. So we talked about, for instance, this example where you have a bunch of cubes in an environment. There's no ordering of those cubes. They're just kind of cubes. And so you kind of want an architecture that can kind of process them without like arbitrarily deciding which one comes first. And as we talked about, there are going to be a lot of papers we talk about later in the class that use transformers. I think, unless I'm super wrong, you won't have to understand the math, like the lower level math super well, or have to implement any of them. But hopefully this is just kind of helpful for, I guess, understanding those papers and maybe using transformers in other contexts. I think there's two like more recent trends in deep reinforcement learning that also sort of motivate why we're talking about transformers. Sorry, I'll get those questions in a second. Those two recent trends are basically like two things that reinforcement learning practitioners are kind of doing more recently that benefit a lot from transformers. One is offline RL, and so I guess we haven't talked about online RL a ton, but basically it is the problem of learning policies or learning how to behave from a very large offline data set. So a lot of the reinforcement learning we're going to be talking about this class is about online RL, where you have the ability to interact with the environment and sort of, explore and collect new experiences. And offline RL, basically you can't do that. And so transformers are kind of useful in that context. And the other thing is also that people are sort of interested generally in using transformers for like multimodal tasks and data. So for instance, if you want to, there's a lot of like cool recent work that will do things with like where the input to the policy is like an image and a sentence or something, and you want to learn to act or do something or other. I mean, in those cases, transformers are actually super useful. Sorry, was there a question in the back there that I missed? Or yeah, you, I guess.
Yeah, for offline I, or like, what is the difference from sequence prediction? The sequence prediction. Like,
yeah. So sequence prediction, right, is basically, I guess, that actually is a baseline in offline RL, right? You might just predict what happens in the data set, and that's your baseline. And I think as we'll talk about later, that is also called like behavior cloning or imitation learning. So yeah, that is something you can do. Offline RL is different because it basically not only tries to copy what it's seen in the data set, but it tries to extract like new and interesting behaviors. So I think the example a lot of people like to use is like if you just gave it an offline RL learner like footage of like, or not footage, I guess, but if you gave it a bunch of samples of like a robot just kind of randomly doing stuff that's not very useful, then ideally if you had like a perfect offline RL algorithm, you might one day discover to like grasp things or like manipulate or use that experience to sort of learn something interesting. So it tries to like, another way of thinking about it is that it selectively imitates. Like it doesn't do the parts of the data set that are like super bad, but it picks up on the stuff that's good. Does that make sense? So like the difference is that if you just did sequence modeling or imitation, you can never do better than the demonstrations you have, right? So if I was learning to drive and I gave you a data set where like 50% of the time it's normal driving and 50% of the time they're just crashing, like if you did an imitation, you would crash 50% of the time. If you did offline RL, in theory, you would just, only imitate the part that's good basically and do that well. Yeah. Another question?
Clarification. So when you say the permutation and variance, I'm guessing you're talking about transformers without the positional encoding part.
Yeah.
Right.
Yeah. So yeah, in practice for like language and stuff, the ordering actually does matter. And so you arbitrarily sort of inject that back in. In RL, sometimes you may or may not need that. So it depends a lot on the application. All right, cool. And again, we went through that very quickly, and I understand that might have lost some people. If there are any questions, please let me know. I think recitations intended to be more interactive, so don't worry about interruptions. Yeah. Anyways, okay, cool. Okay. So it's not all good news with transformers. The bad news and the reason why you won't just throw transformers at every problem in your personal lives is that they're pretty hard to train sometimes. Like they can be kind of unstable. And this problem is especially exacerbated when you're doing reinforcement learning. Again, this is true for a lot of reasons we're not going to go super in-depth on, but basically, actually, we're going to talk about this a little bit in a later slide. But when you're doing RL, basically, you will notice that a lot of the conventional things you did when doing like supervised learning become a lot more unstable and kind of harder to get working for a lot of reasons. And that is all just kind of way harder as well when you work with transformers. Additionally, transformers primarily do well in the regime where they have lots and lots of data and compute, which is really good if you're like trying to play Go or you're DeepMind, but it's not very good if you're like taking a class or something. I would not recommend just throwing a transformer at your problems in everyday lives or training tasks, but it is something to keep in mind that it might be useful. All right, cool. All right, back to stuff that hopefully you've seen before, supervised learning. So I think conventionally, a lot of the architectures that we've talked about can be trained with supervised learning. So in this task formulation, you have like training data where you have like pairs of inputs and outputs. And you basically minimize some loss function using usually gradient descent or some other optimization technique. And the problem is that these networks are sort of not, because they're super big, deep networks, oftentimes it'll be very hard to actually find a unique solution that sort of optimizes over your network. And so in practice, you kind of just settle for having like a local minima, and a lot of the time that kind of works out. And so hopefully people are sort of generally familiar with the idea of supervised learning and how that works with MLPs and neural networks. Something I do want to talk about, which is a bit less mathy, is basically how this will differ when we're doing reinforcement learning in this class. And so one thing to keep in mind is that even though I think people always talk about supervised learning and reinforcement learning as like very separate things, most deep RL techniques we're going to talk about basically do supervised learning in some way. They're just kind of tweaked a little bit, but there's not like some fancy, well, there is one fancy thing we're going to talk about that's very different, but most things are sort of the same, and we'll use a lot of supervised learning for a lot of the class. So TLDR is that if you're very comfortable with like training MLPs using supervised learning in PyTorch, you're probably like ready to take the rest of this class, and you should be in a good spot. I think two big differences that pop up when you're doing reinforcement learning is one that I think they talked about in lecture, is that reinforcement learning involves active learning. And so unlike in normal supervised learning settings, you actually control the data distribution that you're training on. And so this has a lot of implications for like how you train your model. For one thing, it introduces like non-stationarity. And so what this means is basically that in supervised learning, things are pretty well behaved because the data set never changes. And so you can kind of just take your time, I guess metaphorically speaking. But with reinforcement learning, the actual thing that you're learning from changes over time and changes as a direct function of what you're actually doing in the environment. And so this can lead to a lot of instability and basically removes a lot of the nice theoretical guarantees that make supervised learning work. Another thing that I think is a bit different is that supervised learning is basically about like copying something that you've seen or mimicking like labels that are in your data set, whereas reinforcement learning is really open-ended because generally speaking, you don't have demonstrations of the best thing. Otherwise, you would just be doing supervised learning. I like this quote a lot, even though it is like mathematically not true, but I think that it gives nice intuition for basically, why reinforcement learning is different, which is other learning paradigms are about minimization and reinforcement learning is about maximization. Again, that's not literally true because minimization is maximization times like -1, but I think the intuition is good, which is basically that normally when you do supervised learning, the problem is a lot easier because all you have to do is minimize your distance to like some observed thing, but you know what that thing is. Reinforcement learning, on the other hand, is very, very open-ended and doesn't seem like it should be possible. You're kind of just telling your agent to go figure it out and giving it very like poor signal as to how that should happen. And just kind of saying, okay, like do the best you can, right? That's kind of the takeaway. And so practically speaking, really all this means is that reinforcement learning, while the components will involve a lot of supervised learning and it won't do like anything super crazy on that end, it will just kind of be less well behaved. It'll be more sensitive to hyperparameters that you use. You'll have, especially in deep RL, you'll have very few actual like theoretical guarantees that are useful. One thing that if you start reading some of the papers we're going to be talking about, you will find is that a lot of the sort of old theoretical papers that don't talk about deep RL will have very, very nice guarantees, almost none of which are applicable when you start using deep networks because a lot of that theory is thrown out the window. So yeah, that's, I guess, something to keep in mind that these are two very kind of separate things. Okay, any questions about RL or supervised learning? Yeah.
Is active learning like only involves single state or like multiple state?
Sorry, can you repeat that?
Like is active learning only involve single state?
A single state?
Yeah.
Sorry, I'm not fully sure I understand your question.
Like 40 on magnet is like single state, right? Like the state array is not.
I mean, I think active learning is kind of, is it active learning if you don't have a state? I mean, the idea is basically that like, when I say active learning, all I really mean is that like you have to basically control the states that you observe during training time, I guess, if that makes it, I don't know if that answers your question, but I guess in the context of bandits is kind of not active learning because you are exploring, right? Like you do like make inferences about where you are, but you're not actually changing where you actually are. Like when you explore in bandits, the slot machine doesn't change, right? But you change, your beliefs about it change. Active learning would be like if based on how you did bandits, you went to different slot machines. They had different dynamics and that's what RL is basically. Yeah. All right, cool. Any other questions? Anything? Okay, cool. All right, well, that is all the deep learning background stuff that should be useful for this class, plus a bunch of extra stuff that you won't need to code, but might be useful to know. All right, PyTorch and TensorFlow. There is a demo that we could go through, but given the feedback from the start, I'm leaning towards not doing that. It will be on the website if you want to take a look at that. So there's basically like Colab notebooks that will walk you through the basics of how PyTorch and TensorFlow work. Yeah, that's just, these are some resources that might be useful for you. And again, for homework 1, none of this will be used. Yeah.
Do we need to have both?
No. Yeah, I guess pick whichever one is you are more comfortable with. I personally prefer PyTorch. I don't know about you.
Yeah, I prefer PyTorch too. I think all the homeworks have both a PyTorch or TensorFlow option, so you can implement it in either.
Yeah, you can do whatever floats your boat. Yeah, I'm hoping. Well, I'm guessing most of you have already picked one that you like more, but if you haven't, I guess loosely speaking, and I'm saying this completely unbiased, I've heard that basically like within academia, a lot of people like PyTorch more because you can kind of iterate faster, but for like industry applications / like actually doing things quickly, TensorFlow is a bit better. So anyways, all right, cool. I think that's it for my part. You want to switch over? All right, cool.
All right. So, so these are a couple of useful functions in OpenAI Gym. You can look at the slide for reference when you're doing your homework, and then later we're going to go through a short demo on how to use OpenAI Gym. So yeah, most of these are pretty self-explanatory, and you can read the documentation for more methods. But for now, I'll show you how it's used. Okay, so yeah, to install OpenAI Gym, you just do a normal pip install. You might need to install Pygame too. Sorry, do you have a question?
Make the text a little bit larger, please.
Oh, yeah. Is that better? Okay. Okay. So, firstly, what is OpenAI Gym used for? Well, first, it's a Python library used for developing and comparing reinforcement learning algorithms. And so it provides a standard API to communicate between the algorithms and the environment. So rather than focusing on, creating the environment dynamics, you can just focus on creating an algorithm to explore environment or exploit things and compare to the other things that you do. And this is used in a lot of papers that we'll be looking at in the future. So many popular environments like Brick Breaker, the cart pole environment, which will be in a lot of our homeworks, the mountain car environment. These are all just like sort of different games that you can evaluate your algorithms on and compare performance using that. So to do that, first, you just create an environment using gym.make, and then you specify the name of it. For the first homework, it's called the Frozen Lake. Later, we may be using cart pole. So there are different options. And then the beginning state is often found using reset, the reset function. And as you can see here, if we were to print the state, the action space, and the action space sample, for this environment specifically, the state is the cart's position and velocity and the pole's position and velocity. And the action space is 2 because you can either go left or right. So just briefly, this environment, the game in this environment is moving the cart either left or right to make sure that the pole stays balanced. And if you were to take a random sample from this action space, we could get either 1 or -1. And in this case, we've got 1. So yeah, and then the observation space would, as it says in the comments, it'll provide the upper and lower limits of the values it can take, and then also size of the observation space, which is 4, as mentioned before. And the action space, again, would be 2 because you can go left or right. Okay, so in this function, it specifies how a policy would be used in these environments. So we start with the initial state by doing a reset, and then in 200 iterations, we take an action by providing a state into a policy. Remember, a policy is mapping from states to actions. And then we use the step function to basically do that action, and then it gives us the state that we're now in by doing that action, the reward, if we're terminated or not, and some other information as well. So you can see how that would be run. So as you can see over here, we're taking 200 actions, and as the cart moves and the pole is becoming less balanced, we're trying to go in the opposite direction in order to continue to balance it. Yeah, so you can use this notebook for reference afterwards, and these and the slides in the previous slide, the functions that I provided, these ones here are pretty much all you will need to use in the homeworks, especially the first few ones. But yeah, you can read the documentation for more methods. Are there any questions about OpenAI Gym? Yeah.
Do we need a GPU runtime?
No, I'm pretty sure everyone was able to run it in yeah.
Can you explain observation space again?
The observation space. So that's the observation space provides like information about the state. So for example, in the cart pole environment specifically, the state would be the like cart's position and velocity and the pole's position and velocity. But in a different game, it could be like if it was chess or something like that, it would the space would contain like the positions of different pieces on a board. So it's just like a representation of like, the state of the game.
All right. So in the cart pole example, the observation space was just 4 numbers.
Right.
All right.
Yeah.
Got it.
Were there any other questions? Okay. So then another part of your homework is implementing multi-arm bandit algorithms, and I'll just go over the different algorithms there are and how they are different from each other. So remember that the main difference between all these algorithms is the way that they explore versus exploit. So if you have different actions, like you can pull bandit 1, 2, 3, or 4, you will form an estimate about how valuable that each bandit is. And the greedy action would be picking the one that you think is the best at a specific time. So you can either exploit by picking the best action, which is the greedy action, or you can explore and try something else in order to find out if that might be better. So this is a sort of overview of the different algorithms. The first is the most simplest. It's the epsilon greedy one. And this will normally always exploit, but there's a small probability where it chooses a random action to explore. And it's the simplest algorithm. That's why it's used. But over time, you will continue to explore bad options, which is not something you want to do, because the probability of choosing a bad action or exploring does not change over time. So it has what's called linear regret. You will find like the specific formulas on the lecture slides, but this is just a sort of recap. Then another algorithm that you have to implement is called optimistic initialization. So that works by setting very high values for the rewards, much higher than what they would actually be. And over time, when you average out what the actual rewards are, your estimates for a specific bandit would get lower and lower. So the advantage that this algorithm has is that exploration will be reduced over time, because you're always going to pick the greedy action. And eventually, when you average out the results, certain bandits will have a better reward than others. And that's the one that you're always going to pick. Then you have UCB, and this sets an upper bound on the true value of the action. And over time, you'll see, if you were to look at the formula, you'll see that over time, this bound becomes smaller as an action is picked, because we are more confident and more certain of what its actual value is. So another benefit this would have is exploration reduces over time. And lastly, there's Boltzmann exploration that uses a probability distribution to pick actions. And that's very similar to, that distribution is very similar to a softmax function. And of course, if you're using a probability distribution, that can also balance exploration and exploitation, because there is a chance that you don't always pick the best action. So yeah, that's an overview of all these bandit algorithms. Can anyone think of a situation in which, or like a type of environment in which some of these algorithms would be better than others? So as you can see in the bottom three, exploration would be reduced over time. Is that always a good thing? Or do you think there are situations in which you want to keep exploring even after you make better decisions? Yeah.
If you have an environment that has a radical change later on,
Mm-hmm.
you want one that's able to adjust to that?
Right. So if the actual rewards are changing over time, then you want something that adjusts to that. That's yeah.
So does the Boltzmann sort of would it change its exploration if the environment changed, or does it?
So it's a probability distribution that continuously gets updated. So in that case, it would it would, if the true rewards were to change, the amount that explores and exploits would also change. Yeah. I think that's all I have for the bandit algorithms and OpenAI Gym. Are there any questions about any of it?
Yeah, so next week I think is the bandits only recitation, so there'll just be a lot of that and like homework specific stuff. Since this is the first week, I think we're gonna call it. If people have questions, we'll be around for a little bit, but otherwise, I think you're good.